next keynote is on neuroengineering, past, present, and future. And Courtney Lane will be, of Anacapa Clinical Research, will be the speaker. Courtney is an old friend of Rice. She did her undergrad here back in 1996. And then she went off to MIT to get her Ph.D. After getting her Ph.D., she came back to Rice in 2003 and worked with Don Johnson on hearing aid research. After that, she went back east to Boston Scientific and worked on various types of neurostimulators and did that work for several years with Boston Scientific and also with another company, Axonics Modulation Technologies. More recently, she's been developing new biomedical devices for neurostimulation as part of her current company, Anacapa Clinical Research. Courtney, welcome back.
Back. I feel a lot of nostalgia just walking around the campus. I was thinking about my old walk as I used to walk across from Hampton over as a freshman to the Shepherd School of Music. What I've noticed is there's a whole lot more stuff between those 2 points than there was when I was a student. When I was a student, much better? Yes. Good. When I was a student, all of that green stuff was green stuff. And so when you walked past it, you would see open fields of wheat, pineapple fields, and then you'd have to run past the bison really quickly. So it's been a pleasure to see all the changes that have happened over time. So I want to talk today a little bit about neuroengineering and its past and its present and its future. And give you a little bit of history and sense of where we've been and where we're going. And this has really been a passion of mine for some time, as many of you know. So I'll see if I can share some of that passion and excitement with you folks. I think the brain is really fascinating. I think it's just exquisitely interesting. It is, if you think about it, the most amazing processor of information and signals, and it's electrical and it's chemical, it's even mechanical. And so it's got all these things going on. And so I've been fascinated about it since I was a kid. But there's so many ways and things going on that there's a lot of ways that the brain can go wrong. And so we need to think about how do we fix those things. The brain is a part of us, and it's so connected to what we are as humans that the diseases of the brain, whether it's dementia or autism or schizophrenia, depression, Parkinson's disease, all of these things are the kinds of diseases that actually scare us the most because they're so intimately tied with what it means to be human. One example of how technology is changing the way we think about brains is the Deep Brain Stimulation device, which is just one tiny facet of neuroengineering, but I wanted to kind of walk through the history of deep brain stimulation in particular as an example of the kinds of things that we can do. I wanted, for those of you that are not intimately familiar with deep brain stimulators, the idea is that there are leads, electrical leads, going deep into the structure of the brain, and then there's a pacemaker-like device that's implanted in the chest. This is the way it works today, and there's a connection going underneath the skin connecting these two things. This is the first project that I worked on in industry, and I wanted to show you, this is kind of weird, I wanted to show you a video of how this works. This was actually the first industry project that I ever worked on. This man
with your stimulators off, I just want to mark what your tremor is like. Okay, you happy for that to go ahead? Yeah. Right then, with your right hand, if you possibly can, touch your nose, touch my finger.
Standard neurological test. They're trying to touch your nose, touch your finger. You can see that his tremor is basically making him impossible to do this.
Okay, and the real test. Do you think you could pick that up for me? Okay. Should we switch it on? Okay.
Ah,
All right.
ah,
The electrical stimulation is in his brain now.
that's it.
Does that feel better?
That feels good.
Should we try and do these assessments again? With this hand only, and with your right index finger, touch your nose, touch my finger. Okay, you're all right. It's amazing. Good. You all right? Yeah. Can you try picking that cup up for me with your right hand? Well done.
It's incredible. That is amazing. That is an amazing change. For him to even just drink is great.
That deserves a round of applause.
So it was stories like this one that really made me want to pursue this field, wanted me to work hard to bring these products to market. And one of the reasons I was excited to come back today was to share with you where I think the field is going, where we've been, where we're going, and how I think Rice can help with some of these technologies. But before we get to that part, I wanted to share with you some thoughts about neuroengineering and where it came from. The very first electrical stimulation for the treatment of pain and disability was the torpedo fish. And it was documented by Claudius Galen, who was born in 129 AD. And he points out that he thought that the torpedo should be applied alive to the person who has a headache or other pain, and that it would free the patient from pain, as do other remedies which numb the senses. So they've actually been using electrical stimulation with this electrical fish for much longer, almost 2,000 years, to treat pain and disability. But I'll zoom now forward, now to like the 1980s. And in the 1980s for Parkinson's disease, which is what I'll spend a little bit of time talking about, the most common therapy in the 1980s was to actually do a surgical disruption, does this work, of, nope, this, not this one, this one. A surgical disruption of the thalamus, which is this structure right here. So this is a coronal section of the brain. So if you'll think about that for a minute, not only is that structure deep, probably 10 centimeters deep inside your head, but it's also very small. The structures here are about the sizes of small peas, small green peas. And the doctors were trying to go in and surgically resect those pieces of tissue. And you can imagine that if they messed up, then they would disrupt things that they shouldn't be disrupting, which is, quite bad. So one of the first tools that was invented was the stereotactic frame. This is a big halo system that gets strapped to your head, and the patient would be strapped in this contraption, and it would allow the doctor to target deep structures fairly precisely. And they would map the coordinates of the stereotactic frame to MRI imaging or CT imaging back in these days. And they would then use that system to figure out where in the brain to lesion the thalamus. There was one pioneer who realized that even this was not as precise as he would like it to be. So he started using electrical stimulation during these procedures to make sure that he was in the right place before he zapped that piece of brain tissue out. This man was named as Professor Alim Benabid, who's a French physician scientist. And he had this idea of, they were using the electrical stimulation to see if they could make sure that they were in the right place before they lesioned the brain. And then one day he started trying different frequencies. So he did 5 hertz and 10 hertz up to 100. And then all of a sudden, he realized that he was suppressing the tremor using these higher frequency stimulation, higher than anybody had used for this sort of work before. So it actually came up with a transfer function of frequencies that would reduce the stimulation, and used this kind of data to convince Medtronic to turn one of their heart pacemakers into a deep brain stimulation device. So that was the birth of the DBS system. And today, you'll notice that the pacemaker connected to leads model is still very much where we are today. This model isn't ideal because you're still trying to target these tiny little structures that are deep in the brain, and if the doctor doesn't get the leads in exactly the right place, then the stimulation's not where it should be. So it's better than lesioning in the wrong place, but it's still, you went through 4 to 8 hours of brain surgery and you didn't get the stimulation where it needed to be. So for example, Professor Benabid went back to his engineers and said, how can I do this better? And they came up with this. This is a multiplexer. So it's a disc about this big, and he would connect 2 of these multiplexers and implant them in the skull, and then he would implant 5 DBS electrodes on both sides of the brain going down, with the idea that he could then sculpt the fields inside the brain and do a better job of targeting those delicate and small structures. But nobody wants this device, I think, in their brain. So this was 20 years later. So this was 2007. And so we're still in the process of looking for a good solution to this problem of how do we interrupt these abnormal circuits. Today, the most modern deep brain stimulation systems look a lot like this. So this is actually the system that I worked on at Boston Scientific. And the way that they solve the current steering problem, which is what they call it, where they shape the electrical field inside the brain, is by segmenting the electrodes on the leads. And this allows you to push currents in different directions, but still you can really only push the current forward or backwards, or maybe make it longer and shorter. They've made the devices a little smaller, so instead of being this big, they're now that big. They've made them rechargeable, so they last 20 years. And they've allow you now to use computer modeling to at least get a sense of the field that you're projecting into the brain, what that might look like. But I would argue that we could do a whole lot better than this. So where are some ways that we could improve? The first one is to reduce the patient risk. So right now, deep brain stimulation patients, if they want to get the therapy, they have to undergo a surgery that lasts from 4 to 8 hours. And it comes with a risk of 2% hemorrhage. And the hemorrhage could be severe, causing stroke or death. So it's still not safe enough for you to be entirely comfortable going in and having the surgery. Additionally, this has worked really well for Parkinson's disease, but you could imagine that this therapy would work well for epilepsy, for depression, for obsessive compulsive disorder, for a variety of indications. And we've got hints that such a therapy would work, but we still haven't quite figured out where exactly to put the leads, how to program the devices, what really needs to be done. So this is where the future is. For example, on the leads, I showed you segmented leads, but what if they were a little bit polka dotted? And so then you could push the leads, the current, in more directions, or make the shape of the field more interesting. And why do they have to be so big? If right now they're 1 millimeter in diameter, why couldn't they be flat and thin? And then you really could put 5 in at a time without causing so much disruption. Similarly, the battery doesn't have to be this big. It could be much smaller and could go on the head. And then that would also alleviate the erosion and the complications of actually tunneling through the skin underneath your neck. So miniaturization, I think, is key here. Another thought is advanced imaging. So right now, people implant deep brain stimulation for Parkinson's disease based on microelectrode recording. So they do a CT and an MRI scan, they fuse them together, and in the OR, they spend delicate and long periods of time trying to figure out exactly where they are based on the physiology of the system. But there's work where you're using diffusion tensor imaging to figure out the neural circuitry that may be the key to figuring out, for example, on depression, how to target that circuit, how to get those nodes of the system correctly placed so that you know how to program the device and where to put it. Another thing that I find just shocking is that we don't today close the loop. We blindly provide stimulation to this device, but we don't actually sense that we're doing anything correctly. So you could envision a world where you're sensing things inside the brain, you're sensing the person's tremor, you're sensing the person's gait, you're sensing all kinds of things about are they moving, are they sleeping, and changing the stimulation parameters accordingly so that the patient gets much better therapy. And these are very old ideas for us old school signal processors, but they're very novel for the DBS world. Finally, we don't have to do electrical stimulation. There's all kinds of other modalities that you could use for brain stimulation that doesn't necessarily mean strict electricity. Electricity itself is pretty non-selective. When you put an electric field, you stimulate all the electrons and all the neurons in the space. But now with things like optogenetics, you can actually insert and subtract spikes selectively according to certain groups of neurons that have certain genetic characteristics. So I think that's a huge way forward. Similarly, why not sense the neurochemical patterns that are happening inside the brain and actually correct those by then infusing certain chemicals into the brain? And then also helping the brain regenerate itself and regrow some of these cells that are damaged. The thing that I think is so exciting about all of these clinical needs is imaging and tools and smaller devices and feedback loops and signal processing. These are all things that Rice is really, really good at. So for me, I was very excited to see the Neuroengineering initiative at Rice, because I think this is a really great place for the technology to start, for Rice to be very influential on the technology. So I look forward to seeing how we're going to go forward. And I do have an additional ask, not just on the neuroengineering side, but if you folks could also work on teleportation. I don't want to walk past all those buffaloes and pineapple fields and wheat fields again, and I live about 1,600 miles away. So it'd be really nice to drop in from time to time and understand the progress that you guys have helped make. So any questions at this point? Sure. So there's a lot of emerging markets. As I mentioned, people are trying really hard to get new. Rob asked, what is the emerging markets? So interestingly enough, deep brain stimulation, when I started, was about a $300 million market, and it was all focused on Parkinson's disease. Over time, we've had epilepsy just now being approved by Medtronic. It's also approved by NeuroPace. Depression would be a very large market, but unfortunately they've had a couple of failed clinical studies, which is why I have focused my energy on clinical studies to make sure that stuff doesn't happen anymore. But this is well established to be a $1 billion market going forward.
And so also a quick follow-up. So the Cochlear Implant is the most successful neuroprosthetic device.
That's true, absolutely.
That is still true. And so what's the barrier for the other types of implants?
Yeah, good question. So I did focus here on deep brain stimulation, but I've actually worked in a variety of neuromodulation devices. My first love, as you know, was cochlear implants in the auditory system. That's a very well-established field that could use a lot of innovation. I also have worked on spinal cord stimulation for the treatment of pain. That's a $1 billion market today. Occipital nerve stimulation to treat headaches, peripheral nerve stimulation to treat a whole variety of diseases. I spent 3 years working on sacral neuromodulation to treat bladder and bowel dysfunction, which is another $600 million market.
But the
So these
question
are
is
all-
why those haven't come up to be as successful as a cochlear implant.
So I don't know the numbers. So the cochlear implant was definitely first. That was well established before really even deep brain stimulation. So that's been going on for a while. And it's just it's a really nice objective endpoint. You can tell if a kid is starting to use speech and things, whereas some of these other things are pain is a little bit harder to do a study and to show that it's working. But I think they're all coming up together. And to your point, I think they're also kind of should come back together. Cochlear implants have usually been pretty separated from the others, but I suspect over time they'll start to come back together. Did that answer your question? Oh, sorry.
Can I project? No. I'll try not to project. So you have an interesting experience.
Yes.
Both in the context of a Ph.D., the context of working for a very, very large medical device company, and now in the context of as a consultant, perhaps interacting with smaller companies. So I'm curious for the trainees, what do you think? So I think the perception often is that only the large medical device companies are interested in neuromodulation from an engineering perspective. Is that true, or do you see there to be a larger ecosystem that people potentially could be going into?
So when I was a postdoc here, one of the reasons I left and went to join what was then Advanced Bionics that had just gotten acquired by Boston Scientific was I really had the perception that I really couldn't make much of a difference in a small lab by myself, which, maybe I couldn't. But so working for Boston Scientific was really nice, and getting a really deep understanding of the processes, procedures, regulations, the studies that have to be done. But there's a really huge ecosystem now of startups that are working in this space. And so it's a much more dynamic and fluid environment than it was when I first started. And I think that's reflected in the fact that I'm able to do a consulting business. I have more clients than I can handle, and just have a great time working with all these really smart startups that are trying to get started here.
Thank you for the talk, and I'm really fascinated by the idea that you brought up of multimodality closed loop interactions for kind of next generation neural interfaces. And I'm wondering if you can comment on what you see as kind of the major challenges for exploring things like optogenetics. What are the hurdles and opportunities there, and what kind of timeline should we be thinking about for these types of technologies?
Good question. I think, so let me answer sort of non-optogenetics first, because that's a little different. So I think things like closed loop DBS, being able to incorporate your smartwatch and the various sensors that you've got, even using the electrical signals in the brain. I think that stuff's coming quickly. So that's a 5-year thing that we'll start to see, maybe even faster. If you started to incorporate the chemical sensors, that sort of thing, I think that's a little bit farther out, maybe 10 years. Optogenetics is tough because not only is it stimulation with light, which is not that big of a deal, but then you're also adding the viral vectors that you need to affect the genetics. And I think that is probably longer term. One of the things that, as I sort of alluded to, one of the reasons that I'm very interested in the clinical research piece is that piece has to be done very carefully and methodically, with a lot of appreciation of the risk that not everything will go right. Chris was talking about that, at the basis, everything is a statistical hypothesis test. A clinical study is just one big hypothesis test that costs, $20 million if you don't write the equation right at the beginning. So I've had a lot of success in helping companies think through that. because I really do think that's a challenge. And then the regulatory piece is a challenge as well. I actually think that the clinical and regulatory pieces are at least as hard as some of the technical challenges. Does that answer?
I guess I just had one follow-up about sort of the optogenetics and stuff like that.
Sure.
A lot of what you talk about in DBS, and I know you focus just on DBS, but one impression I have is that a lot of these medical devices tend to show really incremental improvements. And of course, when you have something like DBS, you have something that works, and you want to just kind of improve upon it.
Absolutely.
But when it comes to switching modalities to something like optogenetics, it seems like there is a big investment cost to really get into that, and something that maybe smaller startups may not be able to do, and big companies may not be interested in because it's too large a risk.
Right.
Do you feel that there actually is enough of a return for changing modes completely to optogenetics versus these incremental improvements? And if there is a path to that complete mode switch, what would really give someone that push to say, okay, let's do optogenetics, let's not refine the electrode anymore?
Right. I mean, and that's one of the reasons I was excited to give this talk today, is I really think the universities have a huge role to play in this, because the large companies don't move quickly. The small companies, they need to do one thing and do it well and get it out and get sold. So the really innovative things, I think, will come from the universities. And, we've seen a lot of work. I'm based in California, so I'm very California-centric at this point, but UCSF, Stanford, Caltech, Berkeley are all doing really interesting things in this field, which is why I was really have been pushing Rice or excited that Rice is getting on this bandwagon, because between the government funding and the academics, this is where the innovations really got to come from.
So you talked about the invasive deep brain stimulation, right? So have you also clinically worked on non-invasive deep brain stimulation, and how good is it compared with the invasive one?
So I have not worked directly on much non-invasive deep brain stimulation or brain stimulation. I followed it carefully because it was always in my space, but have never actually worked on a project with it. One of the things that I've found really interesting lately is kind of a hybrid where the implanted components are targeting the structures that are of interest, and then you're kind of going back to the 70s when the power sources are all externalized, and you're talking to those through midfield RF stuff. And there's a big resurgence of those kinds of devices, which I think may be really useful. If you're thinking about transcranial magnetic stimulation, those sorts of things, at this point it's really hard to focus those and make them targeted the way they need to be. But there is some evidence that, say, in depression, just sort of a jolt of energy is actually helpful. So I think there's room for all of these things. Does that answer your question?
I have a question. What role do you think that neuronal computations models will play in this neuroengineering future?
Oh, great question. So I think it's got a huge role to play. So if you're thinking about the image I showed of this was in the device in the clinician programmer. It's a very basic neural modeling program that was acquired by Boston Scientific for some tens of millions of dollars. As those get refined, that can only improve things. And then what you'd really want is a model that showed how the current was flowing through these different tissues and which neurons you want to stimulate. And furthermore, how the circuitry of it all works together. So I think that's got to be a critical piece of this. One of the things I worked on with Dr. Johnson back in my postdoc was actually trying to figure out what the right metric for comparing what a normal neural signal is compared to a modified neural signal that's damaged and then you're fixing it, and how you compare those two pieces of information. So I think all of that is critical to getting this done well. Good question.